Here we are. We are talking about solving logarithms and exponents. We did a little bit of this last week where we found the value of x that makes the statement true. We mostly did that with rearranging. We're going to utilize some of the condensing we did, but also two new properties. Besides the ones that we use for condensing. And then we're also going to use another thing that's not really a property, but kind of. So first one is the property of equality. So we're going to have two things that are equal to each other for exponents. Property of equality for exponents specifically. And this says if b to the x is equal to b to the y, then x must be the same as y. Hopefully this feels slightly intuitive. If we have something with the same base and they're equal, then, well, the exponents have to be equal for them to be equal because we're multiplying over and over, so they have to be the same, exactly the same. So this would be like if we have 2 to the x and this is equal to 2 to the 5th, well, then x must be 5. In practice, it will be slightly more complicated than this, right? In practice, it's going to look more like this. Okay, we could rearrange this using our logarithm properties. We have an exponent, the variable, equal to a number. I know this looks like an exponent, but this is just a number, e multiplied 11 times. So you could rearrange and so you would say, okay, so my logarithm equals the exponent. The base is the base, so it's base e, and then inside the logarithm is the value it equals. And then this simplifies. Use a calculator, you're going to get 11. You could do it that way, maybe that's easier, but because the bases are the same, that means the exponents have to be the same. So you can go straight to this. And now we just need to solve. Adding, subtracting, dividing, all that inverse operation stuff. 5x equals 15 divided by 5. X is conveniently a whole number. It's 3. Is that right? Yeah. Okay, so if the bases are the same, that means the exponents have to be the same. We have a similar property of equality for logarithms. So again, two things are going to be equal. It's a property of equality for logarithms specifically. Okay, and so this says if log base b of x equals log base b of y, then x has to be y. We have two logarithms with the same base. Their innards, the things inside of them, the x and the y, if they're the same base and they're equal, they have to be the same. Doesn't matter what the base is, as long as it's the same on both sides of the equal sign. So again, in practice, this is going to look something like. Do like that. So you could rearrange this. We have a variable inside a logarithm. You could rearrange this, and so to rearrange, take the base, raise it to this power, it equals the inside thing. So e to the natural log of 18 would equal 5x plus 4. This simplifies to 18. And then you would subtract stuff. But this seems more complicated to rearrange it. Why don't we just say, okay, if it's the same logarithm both sides, it's the natural log on both sides, well, then the things inside have to be the same. 5x plus 4 is 18. And then we just need to solve our equation. 5x is 14, divide by 5, x is 14 over 5. And this would give you the same thing, doing it this way. But this is easier, I think. Okay. So what I'm going to do now is I'm going to give you 3 problems, and then I want you to pause the video and work on them, and then check your work with what I work through after you've finished. So A, B, C. Do 5 to the 2x plus 3. Five to the 2x plus 3 equals 5 to the 4x minus 1. Natural log of 2x equals natural log of 6. And then log of 7 equals log 3x plus 2. Okay, so pause the video. Work those 3 problems out. And then when you're finished, start the video back up. So hopefully you pause the video and work them out. So now you can check your work. There's really no use in you just watching me do these again. So make a strong attempt and then check. All right. But basically what we're doing is we're saying, okay, the bases are the same. Exponents have to be the same. And then we just got to solve. So I'm going to subtract 2x, add 1 on both sides. We get 4 equals 2x, divided by 2. 2 is equal to x. We have 2 logarithms with the same base, same kind of logarithm. So it means the insides are the same. So 2x is 6, divided by 2, x is 3. Same thing over here. 7 is 3x plus 2. Subtract. 5 is 3x, divide by 3, divide by 3. 5/3 is x. Okay. So same kind of logarithm, same base. It doesn't need to be 10 or e. It could be anything. As long as it's the same, the insides have to equal each other. Okay. Now here is the extra, the last kind of new thing for today. And then we're going to do condensing and solving those, but that's not, we actually kind of talked about that already. So maybe just a reminder of some properties. E to the natural log of x is just x. And really anything to a log of the same base raised to the power is just that number. Okay. The other useful thing that you can do is if you have, say, e to the x, if you take the natural log of this, logarithm with the same base, well, this is just x. Same thing with regular log. Logarithm base 10, 10 to the x is just x. So I don't, in practice, this is not just going to be x. It might have more stuff up here, but it's useful to change your equation by either raising both sides to a power or taking a logarithm of the power. So what does that look like? Well, these are all problems you could rearrange, but they might be easier to solve this way. Like e to the 2x is 17. I can rearrange this into a logarithm using our rearranging technique. I've got the exponent, that's what the logarithm equals. I got the base, that goes in the base, this goes inside the logarithm. We could rewrite it that way. Or we could just do the natural log of e to the 2x, same base here, equals the natural log of 17. This is going to simplify to be 2x equals natural log of 17, and then we just divide. So x is natural log of 17 over 2. So maybe that's easier. Could also have something similar if we have a natural log or a logarithm of something. Now, normally, I think it actually is easier to just rearrange this problem. But to get rid of this log, we just raise everything to the 10th. So 10 to the log 3x plus 1 equals 10 to the 4th. Just raise everything to be the exponent with the power of 10. This is going to cancel into 3x plus 1 equals 10 to the 4th, which is what we would get if we rearranged it. Log base 10 to the power of 4 equals this thing. 10 to the power of 4 equals this thing. So then I just subtract 1 from both sides. 3x equals 10 to the 4th minus 1. Divide by 3. X equals 10 to the 4th minus 1 over 3. And then your calculator will simplify that, right? This is going to be, oh, actually like an even number, I think. 10 to the 4th is 10 times 10 is 100, 100 times 100, 100 times 10 is 1,000, 10,000 minus 1, 9,999 over 3, I think. Yeah, that seems right. And then this is just 3,333. Convenient. That worked out. I made those numbers up. Okay. The last thing I want to talk about is what we talked about, a reminder of what we talked about last week. Expanding and condensing logarithms. And this used the kind of the formula or the pattern that multiplication turns into addition of two logarithms, or addition turns into multiplication if we're condensing. Division turns into subtraction, or subtraction turns into division. And then, what's the last one? Exponent turns into multiplication, or multiplication turns into an exponent. And we go this way or this way, depending on if we're condensing or expanding. Right, so if we want to expand the natural log of 3x squared over 4, we're going to take the multiplication between these two numbers, turn it into addition. We're going to take the division between these numbers, turn it into subtraction. And we're going to take this exponent and turn it into multiplication. So we're going to end up with more than one logarithm. We're expanding it. We're taking one logarithm and turning it into multiple. So I'm going to take the natural log of 3 and add it to the natural log of x squared over 4. And then the natural log of 3 plus this division is going to turn into subtraction. Natural log of x squared minus the natural log of 4. And then this is going to turn into natural log of 3 plus 2 natural log of x minus natural log of 4. So this is fully expanded. Okay, I turned the exponent into multiplication. I turned the multiplication here inside into addition, and this division, the fraction, into subtraction. And then we also need to be able to condense, which is just going the other way, starting with this and turning it into a single logarithm. So log, these can be any base. It doesn't need to be the natural log. Log of, I don't know, 7 minus log x plus log 2. So I'm going to turn this division, or the subtraction, into division. So these two we're condensing, so all three of these are going to become one logarithm. So log 7 divided by x plus log 2. And then this addition becomes multiplication. Log 7 times 2 is going to be 14 over x. And that would be our final answer. We condense this 3 logarithms into a single logarithm. Why would we want to do that? It'll probably make solving easier in some cases. The main case where you want to use this condensing is when we have something like this. Don't know why I put that in parentheses. Log x minus log x plus 1 equals, I don't know, 7. So I have 2 logarithms, same base, different insides. I can't just move this logarithm over here and make the insides equal because there's a 7. So I need to combine these into one logarithm. So log x divided by x plus 1. Log x over x plus 1 equals 7. I turned the subtraction into division inside the logarithm. Then, now we need to rearrange. So I'm going to do this to the 7th equals this stuff. X over x plus 1 equals 10 to the 7th. Then I cross multiply, I get x equals 10 to the 7th x plus 10 to the 7th. This is going to be kind of a ridiculous number. I can let's subtract the x over here and subtract the 10 to the 7th over here. So negative 10 to the 7th equals yeah, this is kind of weird. Uh, 10 to the 7th minus 1 times x. So x equals negative 10 to the 7th divided by 10 to the 7th minus 1. Really tiny negative exponent. Or really big? No, it's still smaller than 1. Really close to 1. Pretty sure that's right. Okay. But the gist is the same. We combined these two logarithms using our logarithm property. So we did subtraction into division. Then we rearranged and then used cross multiplication here and then solve for x. Okay. So here's what we're going to do. You're going to complete the form. If you have time, work on the homework. And if you still have class time left, work on mathematician paper. I think I spelled this wrong, but so complete the form, work on your homework. I want you to do the homework before the test on Friday, right? So we have a test Friday. Finish the homework before then, so work on it in class right now. And then if there's still time, or if you still need to, you can work on it later. And then if you finish this, if you still have time left over, work on your mathematician paper due next Friday. Okay. And that's it for today.